Hello, everyone, and welcome to today's webinar titled Development of an Extraction-Free Saliva-Based Workflow for SARS-CoV-2 Detection with the Biomark HD platform. I am Alexis Krauss of Labroots, and I'll be your moderator for today's event. Today's educational web seminar is sponsored by Fluidigm. Now, let's get started. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you would like during the presentation. To do so, simply type them into the Ask a Question box and click Send. We will answer as many questions as we have time for at the end of the presentation. If you have trouble seeing or hearing the presentation, click on the Ask a Question box located on the far left of your screen. I now present today's speakers, Dr. David King, Vice President of R&D Genomics and Product Management at Fluidigm, and Professor Richard Head, Director of the Genome Technology Access Center at the McDonnell Genome Institute at Washington University School of Medicine in St. Louis. For a complete biography on Dr. King and Professor Head, please visit the Biography tab at the top of your screen. Dr. King, you may now begin your presentation.
Hello, my name is David King. I'm Vice President of R&D for Genomics at Fluidigm, and I'd like to talk to you today about the AdvantaDX SARS-CoV-2 RT-PCR assay that we've recently introduced. In thinking about the critical needs for molecular diagnostic testing for COVID-19, there are four essential ingredients that are essential: scalable sample throughput, rapid turnaround time, assay capacity and coverage, and operating efficiency. And those are all achieved with the product I just described. We'll describe in a minute. Fluidigm satisfies the critical needs that I've outlined by enabling throughput using modular systems that can scale to thousands of samples per day. We can alleviate the supply chain issues and supply rapid turnaround time using a new extraction-free method that shortens and simplifies our overall workflow. And when you look at operating efficiency, we can maximize your laboratory budget by minimizing reagent consumption using our key microfluidic technologies implemented in devices that we sell that automate reaction assemblies at the nanoliter scale. So let me focus on AdvantaDX SARS-CoV-2 real-time PCR assay. The assay is accurate, efficient, uses a non-invasive sample type, saliva, to meet the global need for rapid diagnostic testing for SARS-CoV-2 infection. Again, as I mentioned, there's no need for viral RNA extraction with our kit. It's extraction-free. It achieves analyzes 192 samples and controls every 35 minutes at maximum throughput. And it's scalable. With one of our installations, you can scale up to 6,000 samples and controls per instrument or per installation per day. And the workflow at the bottom of the slide is very simple. One collects a saliva, there's a simple sample prep step, processing on our Juno and Biomark systems to generate up to 6,000 samples a day. Let me talk about our regulatory notification. Fluidigm has filed for emergency use authorization with the FDA. The test is being validated by Fluidigm, and we have partnered with WashU on the clinical work for this application. I'm going to talk briefly about our genetics, genomics, and microfluidic systems as a whole. So Fluidigm has been around for about 20 years, and we have developed deep technology and put into the marketplace many products based on integrated fluidic circuits, or IFCs. These are basically microfluidic chips. So on the upper right-hand corner is a view of one of our microfluidic chips. It comprises an area, a region, clear region on the outside of this microfluidic chip where one pipettes samples and assays. And the black part in the center is the business part where we combine and process all those samples and assays simultaneously. So we can process up to 10,000 reactions all simultaneously, equivalent to, let's say, 196 well plates or 96 well plates, all at the nanoliter scale. These microfluidic chips are processed on our platforms, the Juno NGS library prep platform and the Biomark HD PCR, qPCR, and digital PCR platform that utilizes canned reagents or kits that we supply, and then we also supply design services to optimize particular assays for your own use. The Biomark HD is a robust, high-throughput PCR-based platform. It really, again, it enables the operation of our IFCs, our microfluidic chips, and it's been on the market for quite some time, so it's a very reliable, robust platform. We've enabled multiple applications on this simple architecture, from gene expression, genotyping, sample ID, copy number variation, digital PCR, and now our first diagnostic product, viral RNA detection. Our microfluidic chip, or integrated fluidic circuit, as I mentioned, this is a closer-up view. You can see where the assays and samples are pipetted into the architecture. This is basically the same size as a 384 well plate. The well positions are consistent with standard SBS format so that they're easy to use by hand or by automated robotic systems. And the microfluidic chip or integrated fluidic circuit that we've implemented for the AdvantaDX SARS-CoV-2 assay can take up to 192 samples at once. I wanted to highlight that this work was, our work with SARS-CoV-2 was in very close collaboration with Washington University School of Medicine. We both co-developed the assay. We both performed independent analytical validations, and WashU performed the clinical validation. I believe Washington University intends to use this and implement this test to increase testing capacity in not only the university environment, but also the greater St. Louis area. Just a very quick snippet of some of the data that we provided to the FDA. Here we're showing a table of data where we're showing that a limit of detection for this particular assay is down to 6.25 viral copies per microliter of sample. We've also, this is a summary. I think Rich is going to talk about it in a minute, for our product performance and clinical validation, where we have 100% concordance with blinded nasal pharyngeal swabs. It's very important to show that there were no false positives or no false negatives in this clinical data set. As I mentioned, we've worked very closely with Jeff Milbrand and Rich Head, who you'll hear from in just a moment, at WashU, and it gives me great pleasure to now turn the presentation over to Richard Head, who's Professor of Genetics and Pathology and Immunology, and the Director of the Genome Technology Access Center at the McDonnell Genome Institute at WashU School of Medicine. He's going to talk about the development of extraction-free and extraction-free saliva-based workflow for SARS-CoV-2 with the Biomark HD platform. So, Rich, over to you.
So first, I'd like to take just a moment to thank David King and Fluidigm for the opportunity to speak today and to share some interesting results from the recent collaboration that David just described. So, as mentioned, I'm the director of a facility called GTAC at MGI, which is the genomics division of the McDonnell Genome Institute here at WashU in St. Louis. Our lab consists of about 100 scientists, technicians, and support staff. We run tens of thousands of samples per year. We have both research and clinical CAP-CLIA regulated laboratories. And as David kind of gave you a bit of a preview, we've had an interesting journey, and I'm going to go a little bit more into the detail of some of this journey in terms of how we got to where we are today with the development of this assay. So in the late January, early February timeframe, my lab had initially decided that we were not going to engage in COVID-related test development for a number of different reasons. However, around March, we reevaluated that position based on some of the issues that we were seeing associated with assays that were in use both here and really around the world, and began investigating a number of different assay formats that could potentially circumvent some of these key issues that a lot of laboratories were seeing. For example, NP swabs are very uncomfortable for the subject that's having the sample taken. There are supply chain issues that have been reported numerous times, particularly with RNA extraction kits. And for the types of massive scale screening that really need to be going on during this pandemic, cost is also an issue. So we really decided at that point that we would engage in the process, and I'm going to discuss basically a little bit of that path and how we ended up where we are. So based on that starting premise, we first established a set of goals that we sought to achieve in the process of getting to an assay that we thought could address a number of these issues. So first, we were interested in something that would allow for serial testing, meaning repeated tests with something other than NP swabs, as we know those are very uncomfortable. Self-collection was something that we thought would be advantageous because we obviously would like to reduce the risk to healthcare workers. We were cognizant of supply chain issues. Large-scale testing combined with impacted production from the pandemic has led to a number of supply chain issues. The throughput, sensitivity, and specificity were all issues that were key in our mind, that this had to be very sensitive, very specific, and we really wanted something that was very high throughput to drive the usefulness as well as our trust in the assay, and eventually, and also finally, low cost. I mean, economic factors have to be considered, especially within academic institutions like ours when we're doing very large scale, but particularly repeated large scale testing. So we made a few decisions based on those goals right out of the gate. First, we decided we were going to pursue a saliva-based test. As I mentioned, this is something that we thought would be much more comfortable for serial testing and therefore likely lead to better compliance. We also thought it was much better suited for self-collection. We also then chose to pursue an extraction-free route. So RNA extraction kits have been subject to supply chain issues, as I've mentioned a couple times. And so we really thought an assay, if we were going to work in this space, we really wanted to try to get to something that was going to be extraction-free, which also helps reduce costs and processing time. And our eventual goal was to get to something that could be used for workplace screening. Now, the assay that I'm going to describe today is being reviewed by the FDA as a patient testing assay, but it is definitely our goal to eventually get to workplace screening with this assay. So our first attempt was not actually with RT-PCR. Our first attempt was with RT-LAMP. If you're not familiar with RT-LAMP, this is the reverse transcription loop mediated isothermal amplification, which is a bit of a mouthful, which is why everybody calls it RT-LAMP. This has been around for quite some time, and it has been used quite often as a POC test where central testing facilities are not available for a number of different reasons. It requires very little lab infrastructure. The assay is very, very simple. It's very rapid. It takes less than an hour to run, and it's fairly flexible. It can be done as a colorimetric version, just in strip tubes or regular tubes, or it can be done as a fluorescence assay, say on a thermocycler instrument. And so there was a lot of buzz about this early on, so we started to do some development in that space. We looked at a number of different primer sets, actually 5 different sets of primers that we first did some testing with. And we also started with the colorimetric enzyme mix, and we were looking at a couple of different regions that turned out to be the best in terms of detecting SARS-CoV-2. And so that work actually went relatively quickly, but what we noted right out of the gate was that when we looked at inactivated viral particles in water, the assay was far, far more sensitive than it was if we put those same inactivated particles in saliva. So this sort of presented the first challenge, and we knew this wasn't just a challenge for LAMP. And I think many are very familiar with this, that it's sort of known there is something in saliva, and it may be more than one thing. So there may be things in saliva that are inhibitory to these types of reactions, and not just LAMP. This has been known for some time in the PCR space as well, that there are some types of agents that are present in saliva that just really inhibit these types of reactions. And so we verified that with LAMP as well. So we basically made it our mission to try to investigate many different types of pretreatments on saliva that would allow us to actually get the sensitivity out of the assay that we desired. So after testing many, many different combinations, there were some actual beneficial combinations that we identified. And in fact, some of this is in a preprint, which is on medRxiv. And some of the data that you see on the left of the slide, or information you see on the left of the slide, is from that preprint. And most of these combinations of things involved both diluting the saliva as well as heating it. Many different types of times of heating, temperatures of heating, et cetera, were tested. And then some of them also involved additional reagents, such as adding things like proteinase K and some other reagents as well. But again, as I said, most of the beneficial ones involve some type of dilution and heating. That really seemed to be the key, and then eventually a stabilization buffer for the RNA as well. So our preliminary testing, we were able to get to 10 to the 3 particles per microliter very, very quickly. In this assay, there's about 3 microliters of input, just as a reference. And eventually, with a little bit of testing, it didn't take us too long to get down to where we were seeing reasonably good results at about 10 to the 2 particles per microliter, or roughly 100 particles per microliter of input sample, with about 3 microliters of input total. And we were doing this initially, as I said, in strip tubes in the colorimetric format. So these early results were promising and suggested that we might be able to do this in a higher throughput format, and that maybe we could target, something in the 10 particle per microliter range. So that led us down an additional component of this path where we tried to take this into a high throughput format. And the conversion to high throughput was relatively straightforward. We did find that when we switched to 96-well plates, that the conditions that were optimal in the strip tubes were not as optimal in the 96-well plates, and vice versa. But different combinations of the upfront processing did seem, we were able to find different versions for the different formats that seemed to get us to pretty much the same level of sensitivity and specificity between the two, the high throughput and the low throughput formats. The other nice thing about the 96-well plate format is not only could we do colorimetric with a plate reader, we could also have a fluorescent readout. And actually for LAMP, which isn't necessarily the focus of this presentation, it turned out the fluorescent readouts were better. Again, we had robust sensitivity at about 10 to the 2 particles, or 100 particles per microliter of input. But what you could see from this graph is that once we got down to the 10 to the 1 range, the results started to get highly variable. They were also very dependent on the amount of heating time that was involved in the assay. There's about a 30-minute heat step. And if you go a little bit short of that, you can get false negatives. If you go a little bit long from that, you can start to get false positives. So we kind of ran into this problem with overlapping false positive, false negative range, and it was really, really dependent and very sensitive to the timing, which created limits for us. We were trying to develop this as a clinical grade assay. So that type of sensitivity to a particular component of the assay, we knew was going to be problematic. So we kind of reached a rough barrier of about 10 to 50 particles per microliter of input. And in that range, we had this issue of competing false positives, false negatives that we could not completely eliminate. So this kind of brought us to the conclusion of where we were with this this original foray into the assay development realm, where we had an assay that looked very promising on a lot of initial factors. You know, LAMP was very fast, it's reasonably scalable, it's very flexible, it's incredibly easy to use, and it's very, very cost effective. But there were problems. We really could not get to consistent sensitivity below 100 particles per microliter of input, roughly, you know, give or take a little bit. And once we got down into the 10 particle per microliter range, the sensitivity specificity were fighting back and forth with each other, and we really couldn't get a clean cut in that range where we felt confident. So our conclusion was this is probably very well suited for a point of care device. Something where you have higher viral loads, you're working with symptomatic individuals, you know, and so that might be a great avenue for LAMP, but after the 2.5 months worth of effort, we could not get this to something we considered to be sufficient for clinical grade testing below 10 to the 2 particles per microliter of input. So around early May, we had a significant change in direction. We had an initial contact with the Fluidigm team and basically found that they were working on some kits that could potentially be useful for this application, which you've already heard a bit about. And we were interested. Given that we couldn't quite reach what we needed to get to with LAMP, we decided this might be a good avenue to try. By mid-May, we were already beginning to test samples. So we had some contrived samples that we had generated, and we tested those with Fluidigm with some of their different RT preamplification conditions. And we were looking at viral N1, N2. These are the CDC primers, basically, that are available from IDT for N1 and N2, as well as human RNase-P as a control for the host. And right out of the gate, we noticed very remarkable sensitivity. We had no trouble immediately getting to 10 to the 1 particles per microliter of input. Now, this is a little bit more input. These are 5 microliter inputs for the STA step. But still, this was a fantastic result, basically, given that we had just started. So by mid to late May, we were getting reproducible results in our hands down in that range. And as you'll see, we actually got a little bit below that range for our EUA. And by early June, we were running our testing, our validation testing for our EUA, and we had generated all of our data and submitted our EUA by mid-June. So David had mentioned a bit of this, and this is sort of the workflow, our workflow, and it fairly closely matches what you saw in the previous slides. So we have the samples collected, and those go into a pre-treatment step, which is quite straightforward and relatively simple to do. And those pre-treated samples then go into the STA for preamplification. Those are loaded onto the Fluidigm 192 by 24 IFCs, which use either the Juno or RX controllers to load the chip, and then they go onto a biomark where there is machine-readable data and, in fact, software that we use from Fluidigm to make the positive-negative call determinations for the assay. 5 microliters of input is all we need for the assay at the STA step. And was mentioned, we actually run this with the 3 assays individually for the RT-PCR on the biomark, and we do those in quadruplicate. So for every sample that we put onto an IFC, we have each assay in quadruplicate, the N1, the N2, and the RNase-P. So we get those 4 readouts, and that's part of our overall calling scheme in terms of the reproducibility for a clinical assay. And then we use 4 wells on the sample side of the ISC for controls. So the validation studies started with a limit of detection. We first had to know where our sensitivity range sort of ended and what our specificity looked like as well. with negative samples. And of course, the only way you can really do this is with contrived samples. So you had seen actually a slide from David that had shown 6.25 as what they observed at Fluidigm, which is exactly what we observed at WashU running the assay in our hands, kind of again speaking to the reproducibility, 2 different sites, using, I think, different control salivas, spiking in our own particles, and basically we hit pretty much exactly the same limit of detection. I'd say there's only sort of some small differences at the very low range, and I'll go into that in a minute, but this was actually very good confirmation for us early on that this was a very reproducible assay. So our contrived samples used pooled human saliva as their base. We added inactivated viral particles in 2-fold dilutions. The table that I'm showing here goes from 100 down to 1.563 particles per microliter of input. But we have actually tested higher and lower than that. But this is the range where most of the useful information is generated. N1 or N2 are sufficient for a positive call. And the particles, as you see here, we've reported them in the table format as particles per microliter of input, or in the bottom graph as particles per reaction. So we know that some labs refer to their limit of detection and sensitivity in both ways. So for the purposes of this talk, I've reported them in both formats. So you can see that we have 100% sensitivity at 6.25 particles per microliter, which translates to just about 31 particles per reaction. But if you look further down the list, you will see that due to the N1 or N2 positivity sufficient for calling, we were still seeing 80% sensitivity at less than 10 particles per reaction, down at 1.5 particles per microliter when we pulled the N1 and N2 information and the eventual calls. We were seeing sensitivity at about 80%, even that low. So the assay was incredibly sensitive for sure. The good news was there were no false positives in the 20 negative samples that were run as part of this chip, and I'll speak a bit more to that with some of the other data. So before we get into the actual validation with the comparator samples from MP swabs, there were a number of other factors that we wanted to look at. So if we're going to run this as a clinical test, we have to be assured that the samples can be delivered to us and still be viable for testing. So in order to do that, in order to determine that, we had to do a number of stability tests. So the first test that we did, which is represented in the table on the left, and I apologize, numbers are a little small and hard to read, but I'll summarize the result. We did a room temperature stability test. We did 3 different levels of particle spike-ins with multiple donors, similarly inactivated particles from 10 to the 1 to 10 to the 3 particles per microliter. And then we looked at we held the samples at room temperature with no stabilization buffer of any kind. This is just saliva with particles in it. That's it. No other kind of buffer, no stabilization whatsoever, basically just sitting on a laboratory bench from anywhere from 4 to 120 hours. And at about 120 hours, we saw just a small hint, maybe a half a CT shift from the 0 time point control, the 0R time point control. So at room temperature in a closed vial with no stabilization, the samples were virtually completely stable for up to 5 days. So this was good news. This at least meant that things could be collected the night before, 2 days before, maybe even 3 days before. Obviously, you don't want to go too far beyond that and have a relevant result, because lots of things can happen in that period of time in terms of the individual. But at least we knew the samples were quite stable at that time frame. But not every sample is going to sit at room temperature. If samples have to be transported in St. Louis or Houston or Miami in July, there's every chance that those samples might be subjected to temperatures much higher than room temperature. So we then did an environmental stability test. So we used room temperature as our control, since we had already done a very extensive test. And what you see in the graph on the right is the results for the 100 particle per microliter, 10 to the 2, of inactivated particles per microliter input sample. So at room temperature, RT, for 100 particles, you can see that basically there was no difference between 0 time point and going all the way out to 96 hours. So basically replicating the result we had had before. Room temperature, these samples are completely stable up to at least 5 days. 96 hours was just 4 days for this test, but clearly it replicated the original result. So that was great. You can see that chilling them, at least not freezing them, but keeping them at cool temperatures also is perfectly fine. 4 degrees Celsius, 39 degrees Fahrenheit, 100 particles was unchanged for 4 days. 35 degrees, we started to see a bit of movement. So 35 degrees Celsius or 95 degrees Fahrenheit, basically a hot day outside in some of the southern states. You do start to see a bit of decline, especially as you get out to the 72 and 96 hour time points. And again, this is 100 particles per microliter. At 10 particles per microliter, we even started to lose a couple of the samples at 72 to 96 hours at 95 degrees, but basically up to 48 hours, the samples were quite stable. Where we really see a decline is at 54 degrees Celsius or 129 degrees Fahrenheit. So this is a sample being left in a hot car on a sunny day. So at up to 8 hours, interestingly, the samples were quite stable. But once we got from 8 hours to 24, and all of those points from 24 hours out to 96 are collected at what we called 32, it's actually 999. There was no read on the Fluidigm instrument. There was no signal. We just set it at 32 so that we would be able to graph it. We use that internally as sort of a marker of no signal coming from the biomark instrument. And so this basically, though, told us that, yes, you could have high temperatures for a short period of time, but once you got past that short period of time, these samples would be compromised. Okay, so the samples are fairly stable for a good period of time, even up to fairly warm conditions, as long as you don't get very warm. Hot, like I said, is the equivalent of being inside of a locked hot car for more than 8 hours. But that gives us good confidence that these samples will be quite stable for transport, assuming you don't have extreme conditions for very long periods of time. However, and we've communicated with other labs who've seen this as well, what the particles do not tolerate all that well is freeze thaw. So interestingly enough, when we basically had noticed that some of our positive controls seemed to have increased CTs over time. And we eventually traced that back to the particle aliquots that had multiple freeze thaws. So this concerned us, and we decided, well, we better do a test for the particle stability that we're using for our controls. And at the same time, this also tells us that if we get real samples, you probably don't want to be freeze thawing those samples very often. That could be problematic. So if you're going to aliquot something out and use it, it's probably good to have a couple of aliquots so that if you want to go back to a sample, even if it's a real world sample, you need to be aware of this, that this is definitely an issue. And not so much with the assay, but with the particles themselves. So we performed the stability study, and what we noticed was each and every freeze thaw seemed to increase the CTs. By 3 freeze thaws, we were losing our low-level control on the chip, which is 25 particles per microliter. By the time we got to 4 freeze thaws and above, we started to lose our high-level controls, which is 1,000. So even with real-world samples, we've seen this, that this freeze-thaw cycles are not good for these types of samples. So this at least establishes that baseline. We know that for our controls, we're going to use fresh aliquots, and we really try to keep our real-world samples at less than 2 freeze thaws because you could lose sensitivity as a result. And again, not due to the assay itself, due to the nature of these viral particles. Okay, once we completed all of that, we finally got to the point of completing our full-on sensitivity specificity comparing to NP swab data. So we had a number of samples collected here under a couple of different protocols at Washington University. where we had saliva that was collected with matched NP swabs. The NP swabs were run through EUA-approved testing, and the saliva for the samples that were in our validation study, all but 3 of those samples, the saliva was collected within 24 hours of the NP swabs. And in fact, I think only a few of those were within 24 hours. Most of those were collected within an hour. So they are, you know, for the vast majority of these, they are true matched saliva NP collections. And just a couple that where the saliva was collected a few days after the NP swab. And within this test set, we had perfect concordance. We saw 34 positives and 34 negatives. As David had mentioned, we saw that 100% sensitivity and 100% specificity. All the positives matched, all the negatives matched. The mean CTs for N1 generally run around 16.5 in these patients. Remember, these are symptomatic patients. And N2 seems to average around 18. It's been known for some time. N2 seems to be a little less sensitive in terms of the CTs at which it's detected than N1 with these CDC primers. And RNase-P mean, which is basically just your human endogenous control, it comes in at about 14. So this was great, and what I can tell you is that we have completed numerous replications of this for our internal CAP-CLIA validation as well. And in processing basically 272 samples for our CAP-CLIA, I think we maybe have seen 2 false negatives on very, very low N positive samples that had actually undergone multiple freeze thaws. Otherwise, we've had virtually perfect concordance. So the WashU scale up looks something like this. So what I put out as the simple workflow is fine if you're doing a few hundred samples a day. It is our intent to eventually get this up to, in relatively short time frame, up to 10,000 samples a week. That's our goal in about the next 5 to 6 weeks. And our eventual target is about 50,000 samples per week within our laboratory. So the samples are collected into 2D barcoded tubes, which allows us to scan those at our intake and accessioning. And we are doing the first 3 pieces of what you see up here in a BSL2+ environment. So we take 48 tubes per rack into a Capitol machine, which can decap the tubes. The decap tubes are then plated onto 96 well plates with an Eppendorf 5070 series robot for pre-treatment. The tubes are recapped and those are stored so that we can go back to those. Remember, this is a clinical laboratory process, so we have to be able to go back to these, at least the positives, for some period of time. We use an EP96 then to do a plate-to-plate transfer after we have applied the pre-treatment protocol to get these to the SDA plate. And then basically everything from there on out is the standard Fluidigm workflow. So this is basically how we're working to bring this up to very high throughput. So in summary, we have been able to develop a saliva-based test with, in my mind, very reasonable volume requirements. 500 microliters is our target volume, but we can do this with as little as 50 microliters of input. Saliva is highly inconsistent from subject to subject, even in healthy volunteers. So, you know, it's the amount that you get, the consistency varies quite a bit, and so the assay has to be very robust for that. And so far, all of the work that we've done has shown that all of those issues can be addressed, and that we are able to get down to even very, very small volumes of input. Again, we only need 5 microliters of the mixture at the end for the STA reaction in the Fluidigm assay. So this is a very, very reasonable volume requirement for the sample. Elderly people and some other folks can actually have difficulty producing a large amount of saliva, especially those who are sick, so we think this is actually very reasonable. Assay scaling with robotics, our initial target, as I mentioned, is 10,000 per week with our eventual target of about 50,000 per week. We're very happy with our limit of detection and stability. We think that the samples will transport quite well, even not necessarily being on ice, especially if they're local. If they have to transport a long way, at least being on ice would probably be a good idea to keep them from any high temperatures. But even if they reach room temperature, that should not be a problem for extended periods of time. Sensitivity and specificity were, again, great. Hundreds of negatives have now been tested without any false positives. We don't actually know what our specificity is yet because we haven't run enough samples to get a false negative with this current version of the kit to be able to call it. But we do know that we're below 1%. We know that because we've already run hundreds without hitting a false positive. We might have had one in a very recent run, but like I said, we'll be well below 1% with the specificity. The only false negatives we've had to this point were actually samples that were collected many days apart from the NP swab. So they're probably not even really false negatives. They're probably cases where the infection has resolved over that lengthy period of time. Another big win for this is, as David has mentioned, there is no requirement for RNA extraction. This really helps with supply chain issues, speed, and cost. And we went from basically nothing to the data that we needed for our EUA submission in about a 4 to 5 week window. So, and that was with us, basically doing initial testing to ensure that our pre-treatment steps were working well with the AdvantaDX workflow. So, with that in mind, a few acknowledgments, credit where credit is due. As David had mentioned, Jeff Milbrandt is our chair of the Department of Genetics and my boss. He's also the executive director of the McDonnell Genome Institute. And a member of folks, Rob Mitra's lab and Willie Buxer's lab, were very instrumental in a lot of the upfront lab work that we did to find these different pretreatment protocols that really enabled samples for downstream processing. Our technology development group at MGI under Bob Fulton, Katrina Fronick and Lisa Cook have done a tremendous job. And then I cannot say enough about Chris Sawyer, Lauren Berzia, and Shelley O'Laughlin. So Chris and Lauren developed and did all of the assay testing to get and everything, all the data that you saw generated here today. And Shelley basically wrote almost our entire EUA. So, and they're both in Mike and Lucinda's lines here at the MGI, and of course the Fluidigm team. So on that note, I will stop. And if there are questions, I believe there will be somebody available to answer questions from the talk.
Thank you, Dr. King and Professor Head, for your informative presentation. We will now start the Q&A portion of the webinar. I would like to introduce Dr. King back and Shelley O'Laughlin, who will be answering questions on behalf of Professor Head. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen. Now, let's get started. Our first question is, which are the advantages of using saliva versus nasopharyngeal swabs?
So perhaps I'll answer that question. This is David King again. I think from our perspective, saliva is a much easier to use sample matrix. On the collection side, one doesn't need any PPE. It requires self-collection. Compliance is going to be much higher than using nasopharyngeal swabs, especially either self-administered nasopharyngeal swabs or healthcare worker nasopharyngeal swabs. There's also the issue of supply chain. So as you heard throughout this presentation, we have worked to eliminate extraction as part of this effort. And the reduction in the amount of reagents used and the number of reagents used and the control we have over our entire supply chain eliminates extraction-based supply chain issues. So those are sort of the main areas, main advantages of using saliva over nasopharyngeal swabs.
And Dr. King, it looks like we have another one for you. Which is the maximum throughput achievable, and what do you need to achieve it?
Sure. So maximum throughput achievable with the workflow that Rich and I both have described is up to 6,000 samples per day, and that's a 24-hour day, 7 days a week. It can be achieved with one of our Biomark HD systems, one controller, either a Juno or an RX controller, and a couple of 96-ball plate thermal cyclers. It's very simple workflow, and it's very, very flexible.
And now, is your test a multiplex test?
Yes. So we simultaneously detect, well, it depends. Let me explain what that means. We simultaneously detect 3 targets, N1, N2, and RNase-P. The sample is loaded only once into the microfluidic chip, but the targets are amplified in separate compartments of the chip, so there's separate reactions. So thanks to the capability of our technology, we use just a few nanoliters per reaction and perform a large amount of reactions in parallel. So we're able to save really expensive enzymatic material while providing a huge throughput in terms of data points per processing run. So we don't actually have to multiplex in a single chamber. So it is strictly not a multiplex test. It's actually just the same as running each of the assays in an individual well. And so it actually affords a lot of opportunity and reduction of issues associated with complex multiplex tests.
Now, Dr. King, I do have a 2-part question for you. Compared to the LAMP method, which no RNA extraction step is required, are the 5UL pre-treated samples subject to RNA extraction to obtain the quality RNA first, then loaded for this Advanta DX assay? And without high-quality RNA, do you still expect to get accurate results?
Okay, so that's an interesting question. No, there is no extraction as part of the workflow that you heard today for the Advanta product. It starts with saliva and goes through an RT-PCR preamp step without any extraction. So we start with saliva as the sample matrix. The saliva can have quite degraded RNA, so it doesn't have to work with perfectly pure, pristine, high quality RNA, high number RNA. So to answer the second part of the question, we don't screen samples or do anything associated with validation of the samples for the testing or use of this product in terms of high quality RNA. So it works on any type of saliva.
Now, Shelley, we do have a question for you. How many patient samples can you run per batch?
We run 192 in the IFC chip. We do add 4 controls per set of 96. So for just the patient samples themselves, it'll be 184.
We want to thank our audience. We are getting so many great questions today. So let's look for another one. All right. Let's go here. So Dr. King, is the input into the reaction saliva that is undiluted? And how much of original saliva is used per reaction to get the lowest range of detection?
The protocol uses 12.5 or a minimum of 12.5 microliters of saliva. There is no dilution. While we dilute it, we do dilute it 1-to-1 with PBS as part of the protocol, but there's no necessarily dilution up front. So I think that's the answer to that question.
And is the collection just plain saliva, or do you have to buffer in the tube?
No, it's plain saliva. Neat saliva.
And now, what may be in saliva that inhibits the enzyme reaction?
There are a variety of different inhibitors. The EUA data that we proposed has showed just works with neat saliva. We believe that from literature studies in our field and other fields, that inhibition is not going to be a substantial issue for the reaction that we've described. for the workflow we've described.
We hear that tests currently require repetition to get an expected positive result. Why is that happening, and how do we reduce the number of false negatives, but also false negatives? I apologize, that may be a mistype on the question. So how do we reduce the number of false negatives?
So that's a general statement about testing in general rather than the Advanta product that we've just described. In the work that we've described both here and at WashU, we've not seen any issues associated with false negatives. So I should note that we, as part of the protocol, actually do 4 assay replicates for individual replicates of each sample. Our microfluidic chip affords, so when we run 192 samples, as you just heard Shelley say, each sample is actually processed in quadruplicate. And we use that information to really assist in the reduction of any types of false positive, false negatives.
Now, Dr. King, what is the estimated cost per test?
I'm going to have to leave that question up to our commercial team. If you're interested in following up with us and about that, please reach out to Fluidigm. That depends on a variety of different issues in terms of volume and scale of the particular workflow that you're anticipating using. So I strongly encourage you to reach out and discuss that very topic with us.
Great. Now, Shelley, we have a question.
Let me just say, I will say that we are very cost competitive, as you heard us describe the technology in terms of minimizing the amount of reagents that are used and minimizing the volumes that are used. We are extraordinarily cost competitive.
Now, Shelley, do you have any data on concordance with the NP swabs for asymptomatic patients?
No, we do not yet. We have only had clinical patients that have been in the hospital that we have for our clinical studies. We would like to start doing that soon. So.
And Shelley, would it be possible in the future to develop the kit to study copathogens? I
believe so. David,
maybe I should answer.
Yes, better for you.
The answer is obviously yes. As I mentioned, we have plenty of space on our microfluidic chip, so we can run many assays on top of just N1, N2, and RNAsP for, let's say, influenza A, B, rhinovirus, and a variety of other pathogens. We're working with customers constantly to imagine solutions in that space and deliver solutions in that space.
Okay. Now, Dr. King, I have one for you. Is heat inactivation at 90 degrees Celsius and 10 minutes as specified in the instructions for use sufficient? And have you tested this on the live virus?
I believe that question might be best coming from Shelley, but I think the answer is yes. It is certainly sufficient. There's lots of publications demonstrating that that's the case. I think there's a CDC guideline for that, showing that that's requiring that for inactivation. Testing it on live virus would be the case that Shelley. That's really a question for Shelley. It's part of her concordance study for positives that she ran using the assay. Shelley, do you want to maybe address this?
Sure. Yes, we had we worked in collaboration with another lab here at WashU, and they did test it on live virus and said the 90 degrees was great at inactivating it. So we had previously used 56 degrees at 30 minutes, but we found this 90 degree at 10 minutes worked even better.
Great. So let's see if we have time for maybe one more question. Okay. Looks like we've got one more. What is the age profile of the clinical patients used in the validation?
We did not have access to that information.
I think those studies had to be blinded. So
yeah. We didn't have any of that information, for the patients.
Our intended use statement in the EUA is in parallel, is equivalent to what the WashU has, does not have an age element to it. So we did not then study cohorts of patients in different age categories. It works across all age groups.
It looks like that was going to be our last question. We want to thank you both for your time today and your important research. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today and those submitted during the on-demand period will be addressed by the speakers via the contact information that you provided at the time of the registration. Please join the meeting room at 9:30 and visit our COVID-19 diagnostics booth, which is the second row on the right. You can find cost information and any other questions that you may have can be answered there. This webcast can be viewed on demand through July of 2021. Until next time, goodbye.